All right, welcome everyone to our Saturday session of Large Language Models Bootcamp. Today is the 12th of October. It's past 11 in California here. And we are going to be discussing this paper, MovieGen, which just came out. If you notice, the date on it is October 4th. So this is a remarkable breakthrough that one would consider. And that's going to have a really big impact on the video creation world. So I'm going to read this paper, but before I read this paper, for the benefit of those of you who are not aware of what exactly has happened in the last few days, I would like to first take you to the website, the blog website, to see the impact or the outcome that this paper has achieved. So let's go to this particular URL first and start from there. We will do that. Rahi, could you please also make a note that we need to add a little section in which we give the URL to the blog also.
Sure.
Just pass on these notes to Chandel. We'll take care of it. Okay. All right. So when you look at this, what do you see? Does it look photorealistic? Yeah. Not only photorealistic, observe the physics of it. The physics looks right. The ripples look right, are much better than what we are used to, isn't it? If you remember, not a long time ago, last year, whenever we did image generation, and forget about video generation, even image generation, our generated images, the hands used to come out terrible, isn't it? It would have like extra fingers and all sorts of artifacts and so forth. But now we are in a world, in 1 year, we have moved much, much further than that. The state of the art has become this good. Now, you see this flowers and everything, it looks fairly realistic. Observe also that this is not a low resolution video. It is a high resolution video, high def, right? Mm-hmm. And let's look at some more breakthroughs. Look at this picture. This is the input prompt was a girl is running across a beach and holding a kite. She is wearing jean shorts and a yellow t-shirt. The sun is shining down. Okay. So what do you see in this video? Could you point out to some things that look remarkable? First, it looks very photorealistic, isn't it? It could easily have been a video. It's not perfect, but it's certainly much better than the state of the art at this moment. Observe that the motion, the leg motion is rather hard for video generation engines to get it right. AI engines so far to get right. A good runner will immediately tell you that the running that you see from a lot of the video gen is not realistic. The muscular movement, the physics is not right. The action is not right. But here, observe that the action is right. Observe that the shadow cast is correct, that the child is casting is correct. Observe also that her shoes are leaving footprints in the sand properly, isn't it? Observe that there is a breeze that is making the kite actually fly and flutter. The wings are fluttering, isn't it? This is a very high degree of photorealism. Now, also observe that obviously it is not perfect. If you look at the rocks and the hills, you could have perhaps asked for a higher resolution, potentially. But I suppose it's trying to emulate a shallow depth of field. What is near is high res. And as you go further and further into it, it's a little bit more less clear, and it's a shallower depth of field it is doing. Now, this is generating a video just from a prompt. Right? Now, those of you who are into MovieGen, you will immediately realize that if you had to produce this video, how many of you know video generation or do video editing or videography? You would realize that this is itself a project. To take this, if it was really taken, I would imagine that somebody, and I'm just imagining that somebody, and videographers may correct me, you would be running behind her with a gimbal to make sure that your camera doesn't shake. Isn't it? You would be holding a gimbal. It's not an easy shot to take, right? And or with some vehicle, you would be following her. This is more interesting. You not only give it a text prompt, you give a picture. You say this person, a woman is sitting on the grass of a pumpkin patch. She is wearing a scarf and holding a cup. The background is filled with rows of pumpkins. Right? Now, this is the picture. How many of you would have looked at it and realized that this is a generated video? Totally awesome, isn't it? And she's even smiling for you. Right? They added that. Pumpkin patch, somebody looks very happy, enjoying. I suppose that must be a pumpkin spice latte or something, coffee or something. Okay, beautiful. Pumpkin patches. Pumpkin patch, as you know, in US, at least evokes a lot of happiness because most parents take their children to pumpkin patches. Right? It's a happy scene of fall season. So, guys, do you realize that this is not generating a generic video from a prompt? It is generating a very specific video of a person of whom you have given only one image. Think of the potential and think what sort of disruption these things are going to make as these things evolve more to the whole movie industry. Did anybody know about that strike in Hollywood? Right. So you can imagine what's going to happen to their world with all this. Now, it can not only generate videos, but suppose you give it a prompt asking for sound. Does that look like a very realistic movie scene? Right. So you can imagine a scene in some movie traveling through these territories in a storm coming. Now, this is a very interesting video. What it is saying is the picture on the left is a real picture, it's the original picture. What is it? A child is flying a lantern. Right? Now, this sort of lantern, at least in Punjab, is very common. I don't know if it is so common in other parts of the country. People from Punjab, would you agree that you have seen it in your childhood? Yeah. Which particular season you do it? Baisakhi? January, yeah. Baisakhi, right? Sankranti, yeah. It's pretty common. So now what you're asking AI to do, what you're asking AI to do is keep everything the same, but replace the lantern with bubble, right? So observe the interesting thing. A bubble does not have its own source of light. The source of light is the sky. Observe that in the bubble, the reflections come through perfectly of the background. Like, I don't know if you will see it again. You see this reflection that just was there, right? In the bubble. And it's very realistic. Now, this one looks silly, but actually it's saying a lot. There's a lot of physics and the real world realism here. A sloth with pink sunglasses lays on a donut float in a pool. The sloth is holding a tropical drink. The world is tropical. The sunlight casts a shadow. So see, the first part might have been a little easy, a sloth with the pink sunglasses on a donut floating in a pool. But you make it hard. The world is a tropic. The world is tropical. The sunlight casts a shadow. So do you notice the interplay of shadows as the donut moves around in the pool? Right? The next one is even more interesting. This is a person playing with fire, right? Putting up a show on the beach. Here, this is actually from a photorealism perspective, a pretty hard shot to get, right? To video to generate, because you have to get the light right, the fire right. That's not hard. But what is more, because the fire is ultimately there's one fire that's spinning, or one or two, three fires that are spinning in the wheel, I suppose. Look at the ground and look at the flickering of light. Isn't that interesting? Right. Likewise, this is funny one, a fluffy koala bear. It has gray and white coat and a round nose. The surfboard is yellow. Koala bear is holding onto the surfboard with its paws. The koala bear's facial expression is focused. The sun is shining. Now, the reason I found this one interesting is this is a very dynamic shot, very dynamic video, isn't it? There is a lot happening, and you have to have all the transitions right, isn't it? You have to get the waves right. You have to get all of this right. The high of the peak and the troughs of the wave right, the surfing right, and many things. And likewise, there is one more, and this is, you can look into the mirror that the reflection comes through. This is a very cute one. Look at the high resolution that it produces. The physics is right. In a hot spring, you see water steam or water evaporation take place, the steaming take place. And look at the monkey having fun with the little boat. So I'll leave it at that. But now look at this one. You have an original video, which seems to me somewhat like a scene of what would be the background scene? Something like the Death Valley, isn't it? Joshua National Park, yeah, something like that. And this person is running. And you take this video and you say, add pom-poms to his hands. I don't know how many runners do that, but you look at the realism of it. Right? And if you observe the pom-pom, you can literally see the changing color, like the light effects on it. Then the next text prompt says, turn it to a cactus desert. Now, what I found interesting is that if you have been to, this scene to me looks like Nevada, New Mexico, or Nevada or Arizona, one of those desert places, right? On the other side of the Sierras. And if you have been there, you'd remember that the earth tends to be a little bit reddish. Cacti grow, but the hills are completely devoid of vegetation, isn't it? And it seems to have gotten that right. Then for fun, they make this runner wear a dinosaur suit. So this is another one. There's a lady. Now here, the interesting thing is, you see that you don't see the full face of the lady, of the girl, but you ask, can you please remove the VR headset? And it imagines a face that's pretty plausible, isn't it? And then different variations of it. This one, you change. The one that I found background changing is fine, but in his hand, if you add sparkle, notice getting the physics right, because the light of the sparkle now is illuminating his hand and t-shirt. Right? So these things are actually, those of you who have been trying video generation with different tools, you would realize that you're looking at something really powerful. Right? And there's more and more to it. Right? Here is the original video. And then suppose add pouring rain. So here there's pouring rain now. Makes movie making a lot easier, isn't it? So look at this penguin. Ah. So there you go. So, all right, guys, I suppose I've made the point. With this one picture, again, grounded on this picture, personalized, you give a text prompt, a man is doing scientific experiments, blah, blah, blah. In a lab with rainbow wallpaper, the man has serious expression, blah, blah, blah. And how many of you would look at it, would have said that this can't be real? So I hope you guys are realizing that the world is changing. This is multimodal. This is multimodal. This one. Yeah. So guys, this is where we'll end multimodal. I just realized that I haven't covered the diffusion models, the theory of diffusion models. So I'll cover that also today or tomorrow. But today I want it to be mostly labs. What it means is that I want you guys to build something today. Was it fun building something with Lava last time? So in the same way, let's actually build so we gain confidence with all of these things. So there we go. Come again? Okay. So look at the sound effect. You give a text input, rain pours against the cliff, and the person with music background. So here we go. Look at the next one, which I found quite interesting. And by the way, these are generate input sounds. You give it a video and it injects the right sound into it. So you can just take an audio and a video, and it will. See, it's gotten the sound of a skateboard against concrete, right? And so I won't go more into that, but suffice is to say, how many of you would like to know how this is done? So this was, again, not an easy work. It took massive amount of hardware to train a massive foundational models, a set of foundational models. And let us go now and learn exactly what happened and what was done. So this is the paper we are going to read. Do you guys need any break before we continue? Or are we ready? We are ready, right? So we can continue. So the title of this paper is quite provocative. Movies have a cast, right? They're actors. So the title of this thing is MovieGen, a cast of media foundation models. Right? So I love the title. It's very well written. Actually, it's a very well written paper. We present MovieGen, a cast of foundational models that generate high quality 1080p high definition videos with different aspect ratios and synchronized audio. We also show blah, blah, blah. So I won't read the rest of it, but it is important that our models set a new state of the art on multiple tasks. This part is important. Our models show a new state of the art in multiple tasks: video to text synthesis, video personalization, video editing, video to audio generation, and text to audio generation. You saw examples of all of that. Our largest video generation model is 30 billion parameters. You realize that that's a tiny model, 30 billion parameters. Like these days, people are ashamed if they are not working with at least 100 or 70 billion parameter model in text generation. But actually, multimodal models tend to be smaller. So, so you have this, and we show multiple technical innovations and simplifications on the architecture, latent spaces, training objectives and recipes, data curation, evaluation protocol, parallelization techniques, and inference optimizations that allow us to reap the benefits of scaling pre-trained data, model size, training compute for training large-scale media generation models. A very long sentence in which they have put a lot, but actually, this is a very dense statement that needs to be unpacked because they genuinely have a lot of new work, innovations at the level of at everything, like in the architecture. It's a nice new architecture. Latent spaces, those of you who are keeping up with all of the JEPA series of papers that we read, iJEPA, VJEPA, yeah, iJEPA, VJEPA, and all of that. And that whole program, you know that this research group tends to favor doing a lot of the stuff in the latent space. Yeah. You'll see some flavor of that. They're using latent space and so on and so forth quite heavily. Well, I think everything in these days, machine learning is in the latent space, but yes. Training objectives, data curation, they did a lot of that. And from an engineering perspective, they did a lot on the evaluation protocols and the parallelization. They did. This was a massive feat of engineering. Let me just say that this is no joke. It is a massive piece of engineering that has come out. And everything, they even did innovation in the inference optimization, right? So let's go and read the paper. Now, I'll read only important sections of the paper. The first paragraph is very instructive, so I'll read it. Imagine a blue emu swimming through the ocean. Humans have the astonishing ability to imagine such a fictional scene in great detail. Isn't true? The moment I say anything, like somebody tells you a narrative, your mind goes and imagines the entire scene, right? Whether you like it or not. Implicitly, you have a video that plays in your head, right? Human imagination requires the ability to compose and predict various facets of the world. Simply imagining a scene requires composing different concepts while predicting realistic properties about motion, scene, physics, geometry, audio, etc. See, each one of these have to be right. Otherwise, it won't be realistic, right? And your mind automatically does that, right? Equipping AI systems with such generative, compositional, and prediction capabilities is a core scientific challenge with broad applications. While large language models aim to learn such capabilities with a text output space, right, which we know. What's the output of a LLM? Tokens, word tokens, right? Yeah, so tokens aim to learn such capabilities with a text output space. In this paper, we focus on media, image, video, audio as the output space. We present MovieGen, a cast of media generation foundation models. MovieGen models can natively generate high-fidelity images, videos, audio, while also processing the ability to edit and personalize the videos. You saw that. You can actually take a video and edit it. Now, they go into all of this and they give you the sizes of the various models. So they say that there are basically 4 models that they built. One, they built the MovieGen model. Which is a 30 billion parameter model. Then they built, let me call it A, B. Then they built a second model, which is the audio, MovieGen video model, sorry, video. MovieGen audio, which is a smaller model, I believe 13 billion parameters. Then they do, I would call it personalization. C is personalization of number 1. And the D, they give editing model for number 1. You can edit a video. You saw all of that, right? The marathon runner you could replace. Yeah. And personalization you saw in the pumpkin patch, right? So this is it. So we will learn about how to fine-tune and personalize and how do they do that. So here are the key contributions, which we will talk about, and then we look at the architecture. We achieve these wide capabilities using 2 foundational models, the MovieGen video, a 30 billion parameter foundational model for joint text-to-image and text-to-video generation that generates high-quality HD videos of up to 16 seconds duration that follow the text prompt. Right? So the model is pre-trained jointly on the order of 100 million videos and 1 billion images. Just think about it. This model, just think of the sheer scale of data that has gone into training this model, in which the model essentially watched all of these videos. Right? And we find that pre-trained model can reason about object motion, subject-object interaction, geometry, camera motion, and physics, and learn plausible motions for a wide variety of tasks. Now, those of you who have background in computer vision, etc., know inferring the camera positions, etc., these were not easy tasks, and the geometry. These used to be pretty interesting things that you would do in the subject. To improve the video generation, we perform supervised fine-tuning. This is important, on a small set of curated high-quality videos and captions. So at the end of it, to make sure that the pre-trained model actually works well, you take a gold data, like sort of small set of really high-quality data, what you would call gold quality data. That's what we all do. And then make sure that we fine-tune on that, right? Because there we know the answer, which is supervised fine-tuning. Why? Because if suppose I have a video and the text is described, and then I do video generation, I can have a loss function that compares the two, isn't it? So MovieGen audio, 13 parameter, is a smaller model, and personalization is, we saw that, and video editing. So how do they do that? It's a technical paper, guys. So by now, you have the foundations after going through blip and lava and all of that and clip. You should be able to understand. You do text to image is easy. You first generate a text to image, 256 pixel training. Then text to image and text to video pre-training. So you have pre-train it, like by giving text prompts and generating videos, right? Up to 16 seconds at 16 frames. So what will you get? You'll get 256, like you'll get a 256 pixel image. If you do, you'll get a video of 256 pixel. You need to upscale it, 256 to upscale that. And after that, you basically you produce these videos, then you do personalization, text to audio, you need to make a model, you need to do further fine tuning and so on and so forth. But you realize that this paper says, and the videos you saw was high def. It was not just 768 pixels. 768 is not high def, right? So, but this machine is producing only 768. So what's the gap? They have a upscaling or a super resolution step after this. They put it through that. So here is the architecture. I'll go over it that they do. This is, we train our generation model on a spatio-temporally composed latent space. So what does that mean? We know what autoencoders are, guys. How many of you would like to know what an autoencoder is? Okay. Autoencoder is something interesting. It's a neural architecture whose job is to learn interesting representations of the data. And I'll give you an example. See, suppose you create a neural network. See, suppose, and you can use whatever, CNNs, feed-forward networks, or transformers or whatever. Suppose the input is X dimensional or D dimensional, capital D dimensional, right? Now, what do neural networks produce? They are essentially functions, right? A neural network at the end of the day, you can think of it as some magic function. It does something. It learns function. So it will produce a vector, a latent vector, let me just call it Z, in belonging to some other dimension. Let us call it Q dimensional vector. Are we together, guys? Yeah. It will produce this vector. Now, sometimes the data that comes to you may not be the right representation of the data. And using using a function like this, you may choose to, the purpose is to discover a better representation of the data. For example, data may be very high dimensional. Most of those dimensions may be nonsensical. You want to reduce the dimensionality. So think of it as dimensionality reduction as one idea. So one type of autoencodings. Now the thing is, how do you train it to learn such good representation? What you do is something quite interesting. You take a counterpart. You take a counterpart, call it G of Z. And this will produce some output, right? This output deliberately we'll call X prime, right? So you realize that Z is this network. This network is called the encoder network. It encodes it into a different representation, Z. And this is called a decoder network. Right? And what will X prime be? G of Z, isn't it? And therefore, this is G of F of input. And in some sense, you can say that as far as you're concerned as a black box, this entire neural network is this function, G of F. X goes in, X prime comes out. Are we together? Now, why would you want to do that? Suppose I put a constraint that, see, you can take an X, do all sorts of transformations, but what should come out should be as close to X as possible. All right. So imagine that you're saying, I have a box. I send in X. What comes out, X prime, and I say X prime should be as close to X as possible. And inside it, you can put some sort of a network, neural net. What is the easiest way a neural network can do that? It can just learn to copy things over, isn't it? So if you it can, and we see that. You may say, well, no, wait a minute. Are there not activation functions? And won't activation functions create deformations of X? Yeah. There are linear transformations, there are deformations, there's so many things happening. X is lost pretty much in the first layer itself, if you think feed-forward network, isn't it? So how can you reconstruct X? And the thing that we learn is that neural networks are pretty smart. If you give them enough things, they will learn to reconstruct it. But the interesting thing that you do is, what if you make the problem a little bit harder by having G, a Q, remember Z belongs to Q dimensions, right? Is a vector in Q dimensions. Now, if you say Q is less than D, so let's say that you're taking a 100-dimensional vector and you're squashing it to 3 dimensions. Now there is a problem. You just introduce a bottleneck. Machine cannot copy things over, isn't it? And I'll give you a practical analogy for this. See, there are people who have very good memories, eidetic memory. They can remember anything they read. They need not understand it. Then you ask them a question, they will, if it is there in the text, they can answer that question, right? Or in more practically, sometimes you notice that it used to happen in India a long time ago. You would go, I used to go and travel by train, and sometimes in fact, I once remember noticing a college, and there was a huge crowd of people milling around the college. Lots of people and grown-up people, right? And I thought, wow, people are really motivated to study in this place. What is it? And then somebody corrected me and told, well, no. Actually, what is happening is all these parents and other people are here to help their son or their daughter pass the exam. So question papers come out, experts are sitting outside who for a fee will generate an answer. Parents will then drop the answer back to the kids, right? So exams used to be passed by such means, right? So imagine that you sneak in a book. If you ask a question whose answer is literally in the book, you can just look it up, right? But suppose I change the problem a little bit. I just say, I make it more abstractive. I just say, given this long article or this story, summarize it in a page. Now, it is a little tougher. You have to do abstractive summarization, right? You can't just pick and choose a few sentences and put it there. Right? Reminds me of a joke. Somebody said he's very good at speed reading, right? And he said, I read War and Peace in 5 minutes. Now, just for reference, War and Peace is a really thick novel from Tolstoy. So, and then somebody asked him, so what did you learn? Easy. It was about the Napoleonic War with Russia. Right? So he missed the whole point of the entire dimension of the story. All he remembered is that there's Napoleonic War there, right? So anyway, jokes apart, if you're asked to summarize in a page, you realize that you have to understand before you can summarize. Does that make sense? Yeah. It is a task that requires understanding. That is the idea behind the bottleneck principle in an autoencoder architecture or an encoder-decoder architecture. When you squash it down to Z dimension, Z, a Q-dimensional space, and then you say, reconstruct it back, reconstruct the back, original back. How will it do that? It's hard, isn't it? Right? It's almost like you give up, there's a person walking around and then you say, you make a sketch. So, so one easy way I can think of it is that, see, in the crime scene movies or TV shows, there'll always be the sketch artist, right? And there will be a guy who has done some crime and he's being described by witnesses, and the guy will make a sketch. And most of the time, it would look nothing like the original guy. Right? It could look like anybody. But the idea is that a good sketch artist should be able to make a sketch from which you can decode the real person, isn't it? A picture of the real person. So that is a more summarized, compressed representation, right? So, and that happens when you introduce a bottleneck principle. And so you say that Z is a valuable representation of the data. Are we together? You create a representation that requires some understanding. And this architecture, like this, encoder, decoder, it is called an auto encoder because it is self-supervised learning. The loss function is, what is the loss function? That X and X prime should be as close as possible, isn't it? Like if you send in X, X prime. So basically the loss function is the mean squared error in some sense between this. right? So you could just say that it's the expectation value of x minus x prime, right, squared, right? Or absolute value, whatever it is. But let me write it in traditional terms. Right? For sufficiently large data sets, summed over all items, right? This is your mean squared error. Yeah. Go minimize that. This will be your loss term. So this term is called, when you write it like this, or more formally, people write it in a more mathematical notation using expectation value. It doesn't matter. It is called reconstruction loss. These are autoencoders. Autoencoders are very pervasive in lot of these architectures. In fact, when you come, if you have actually taken the foundational course with me, so did we cover autoencoders recently? And did you do the lab on autoencoders? And was that lab impressive, isn't it? Right. So, so what you could do, I'll give you guys an example of the lab. You would give it pictures of trees with all their leaves and other things. It would create a low dimensional representation of it. And then from the low dimension, it would reconstruct the tree, and it looked very close to the original picture, right? And by the way, sometimes these low dimensional representations are really, really low dimensions. So that's the power of autoencoders. They're everywhere. Once you get familiar with autoencoders, you'll see that they show up everywhere. Now, what's a temporal autoencoder? We'll come across it here. But simply put, before we get into it, because you have time series data, because frames, what is a video? It is a succession of frames and an audio. But let's look at the succession of frames. So there's a time dimension also. It is not just an image, but a succession of images that you will sort of project into a lower latent space and then project back to the original space. Right? You have to train your machine. That's why it's the temporal autoencoder. But once you have a temporal autoencoder, the output is the latents. The latents, you can treat it as little patches of your image, patchify. And this is a little Gaussian. Now, see, once you create it, let's read this sentence. Now here, guys, if you are not familiar with some of the foundational architectures, I apologize. This may be a little bit hard if you haven't taken the other course. Now, if you don't get it, don't worry. Or rather worry and go take the other course, right? So let's read this part. We train our generative model on a spatio-temporally compressed latent space, right? Because what will the encoder part of a autoencoder, AE, by the way, is the autoencoder, TAE, what will it produce? It will produce the latent representation, isn't it? Are we together? You take the latent representation and you break it up into patches, that thing you're familiar with, VITs and so on and so forth. So you do that. You have this. And then you notice that you inject a Gaussian noise, right? Why do you inject a Gaussian noise? So that it can be more robust, it can create more variations. Yes. So the answers given are because you can train them better, that you can create more variations. See what happens is, and you'll learn it. This is again, guys, I apologize. This is foundational neural networks. A deterministic machine will produce the same output for the same input, isn't it? But if you want to have, you need to, if you need to have different creative outputs, somewhere or the other, there has to be a latent variable. In other words, sampled offer distribution. You always do that. For example, in a large language model, where was the sampling taking place? In the softmax layer. Remember, in the final decoder of a large language model, you do a sampling of the final layer. We covered that, right? Do we remember that in the study when we studied the transformer and the large language model architecture? We did that. Here, a lot of the image task, and this is variational autoencoders, generative adversarial networks, etc. You do need to start with some noise, and noise is essential. You will take a Gaussian noise and you will shape it. It's a non-intuitive thought. You'll shape it into information, right? And you will notice that this is a very interesting field in multimodal learning. Diffusion models also, you will see, they basically shape noise, Gaussian noise, into a picture using a process of reverse diffusion, right? And we will cover diffusion models also a little bit, but let's go with this. So you inject noise. So now you get an embedding. You see that, right? This is embedding in which space? In the latent space. Okay. So what have you done? You have just injected Gaussian noise. After that, think of a standard transform. You have a text. You pass it through three different actually models, because they must have found out experimentally that it helps. Instead of just one model, pass it through three. It's a full transformer, classic transformer, as an encoder-decoder, as in the original Vaswani kind of, the attention is all you need, something like that. And then there are other variations of it. You pass it through. What will you get? You will get the prompt encoding, isn't it? And now what you do is you do a cross attention between your latents and the text that you gave, right? Make the two come together, and then you have it produce a decoder. Then you feed it the thing that comes out of it. You give it to the decoder because it's still in the latent space. Now you ask the decoder to go decode it back into a picture or a video, produce frames, right? This is the architecture. This is, so guys, so I know that this will be a little bit hard if you don't have background in variationals and GANs or something, or any one of these tasks, but it's not very hard. We did cross attention. Remember, we did cross attention in the original transformer. We did cross attention in the blips, yeah, and so forth. So we are familiar with cross attention. This explains, because this is the cross attention between text and the information coming from image, right? And then you feed it into the transformer blocks and cross basic. This is the standard transformer stack. What will it produce? Transformers ultimately produce latents, right? It will produce some, in some space, it will produce a representation. What do? You take that representation now, and then you say, okay, time to decode it. Undo the process, right? So the interesting thing is that the entire work is done in the latent space. The transformer is working itself in the latent space, itself directly. And then you decode it. And when you decode it, then you do a few other tricks. For example, you produce an image and then you do super resolution of the image, upscale the image. Right? Now, guys, are you would you like to know these technical details, or is it getting too technical? It's good, huh? Okay. So the way now the whole question is, how do you do all of this? There's more detail to it. Let me give you this. So guys, one image. So suppose I have an image. It has a height and a width, right? So every pixel's coordinate is, and then there's a RGB channel, red, green, blue. In other words, there are three frames. Any one picture has three channels. So you need to give the coordinates of every pixel as which channel it belongs to, RGB channel, what is the height, what is the width, isn't it? So therefore, it belongs to a Cartesian space of this dimension, C cross H cross width, isn't it? Makes sense, right? So it's a Cartesian, am I getting it right? Yeah. It is at least, its shape rather, your data shape, therefore, will belong to this, right?
And time also. It's multiple things.
Time, yeah. And now, because you have many frames, there will be time coming in, T also coming in. Does that make sense now? No. Because now you have to ask, what is the temporal location of this image? So that is what it is. That's all it is, right? So now let's read this sentence and see if it makes sense for us. For the purpose of efficiency, we encode the RGB pixel space videos into a learned spatiotemporal compressed latent space with a temporal autoencoder. So they're using autoencoder, amongst other reasons, for efficiency. Doing computation with 1,000-dimensional matrix versus doing computation with a 10-dimensional matrix, the compute costs are hugely different because matrix computations are almost cubic, not quadratic or cubic. Right? Our TAE is based on a variational autoencoder, right? Classic autoencoder, and compress the input pixel space video of shape. So this was the original shape, right, to a continuous latent space. So what they do is they say, suppose there were height was, I'll just take 64 pixel, right? Divide 64 by 8. They take a ratio of 8. So they're compressing it, scaling it down by a factor of 8, right? There's a 8 compression with height. And now the interesting thing is height and width is fine, but temporal scale, which means that suppose I had 16 frames, which is what you do, right? For 1 second, you have 16 frames. Now you got only 2 frames for that second, isn't it? So there's something to know. This compression reduces the overall sequence length of the transformer, etc. The TAE architecture, how does it do that? Very simple, just as you would expect. Now there is a problem. Suppose I had not 16 frames, I had 14 frames at the tail end, let's say at the end of it. Yeah. Now 14, what will the machine produce? It will produce still 2 frames. When you decode those 2 frames back, it will multiply by 8. So 2 frames will become 16 frames. But there were not 16 frames in the original video. So you have ended up with spurious frames. So what they do is they'll discard the last 2 frames, which makes sense. Right? These are minor technicalities. Huh? And now, they also, see, there's quite a bit of work that has gone into it. Some of the things are interesting. I'll mention it. They found that people who were doing video reconstructions like this before, those people used to observe this in this corner. Do you see this thing there, right? Which is here. And now you don't want those artifacts in your video. People were curious, why does it happen? So they seem to have debugged it and found the real reason that it happens. They found that when you produce latents, the latent vectors in the encoder space, then if the latent vector is too far from others, right? If it is too far from others, its size, then the machine doesn't know how to decode it well, right? And it will produce something, which makes sense, right? Outliers become hard to figure out. What is this? Make sense? So what they do is they say that, see, suppose you have a bell curve. See, guys, what is the definition? This is, suppose people are 5 feet 8 inches, right? And let's say that there is a 6 feet 9 inch fellow. How would you know, intuitively say, oh, this guy is very tall? How do you know it's very tall? Compared to the average, isn't it? So you always look at the value x minus mu, isn't it? You subtract the mean and you see, now how do I subtract the mean? You typically use, traditionally people have used the so-called inner fence and the outer fence. Inner fence is at 2 standard deviation because this has a distribution. This is sigma, right? Inner fence is at 2, outer fence is at 3. Now, people say that if the value is beyond 2 standard deviation, the guy is an outlier. This data point is an outlier. It's a soft outlier. Means, yeah, right? So, and If it is beyond 3 standard deviation, then the percentage of people who will be there in a normal distribution will be very small. Like they're real outliers. You can look up, I forgot for the normal distribution.
It's within 3 standard deviations, so it'll be like 0.2.
Yeah, yeah, exactly. Some very minuscule amount of people would be beyond 3 standard deviation. What they do is they look at hard outliers. So R for them is equal to 3, which means that they're looking at hard outliers, not soft outliers, right? So it is there. That's all they're doing. They're saying that attach a penalty term to the machine. When you add this penalty term to the latents that it produces, what you're saying is don't produce outliers in the latent representation. Don't produce these weird vectors that are going way out, far out, isn't it? Another way to do that is keep something within an envelope. All your vectors, latent vectors, within a certain q-dimensional spherical envelope in some sense. Are we together, guys? Right? Keep it within the envelope. Don't let it grow too much. And if you don't let it grow too much, they found that you won't have these artifacts, which itself is a little bit of a discovery. Then, so there's more temporal time.
So Asif, when we say don't let it grow outside of that,
Yeah.
if during the computation, if it falls outside, do they do a remapping or like?
No. See, look at this. This is a loss function term, right? So what happens is when the machine is not, when it is going through training, it will produce vectors that will fall outside, right? When it falls outside, what will happen? This thing will be greater than 0 because it is outside the 3 standard deviation. And so it will add to the loss term, and you're basically telling the machine, you're nudging the machine that, hey, you need to change your weights and biases, your parameters in such a way that you don't keep producing these mistakes. And so this, remember, loss term is valuable during the training of the machine, pre-training of the machine.
Okay.
Right? When the model is being pre-trained, it will basically saying stay within the envelope. This was a mistake. Because that's the best time to, I mean, the pre-training is that. So the magic, see, a lot of the ways to.
And one other question, like when you're talking about these autoencoders in here, right? Are these autoencoders specifically created by Facebook for this, or do we do they tend to use like a, okay.
See, autoencoder is a whole theory. The subject of autoencoders is fairly vast. Let's just say that there are at least, like I can think of 40, 50 significant autoencoder architectures. And I give you the basic idea of autoencoders. And if you come to that foundational course, we cover, how many? We cover a few of the key autoencoder architectures, right? And they have enormous purpose. Actually, once you get used to autoencoders, wherever you look, you'll see an autoencoder sitting there, right? In different neural architectures. You look at—
So in that case, Asif, sorry, like, so in that case, one of the secret sauce ingredient is going to be the autoencoder that they're using for this.
Yes,
for this model, right?
It is so, yeah. You notice that they have an autoencoder. So you look at this piece. This is the encoder part of the autoencoder, and this is the decoder part of the autoencoder. Right? And what they do, in simple terms, right, they take the video and they project it using the autoencoder to a latent space, and they do all their logic, cross-attention, and everything in the latent space. Right? And then they decode it. That's the basic architecture. See, when they say that we use a simple architecture, well, simple is in the eyes of the beholder. When we are getting introduced to it, it is a very complicated, it looks very complicated. But believe me, people when they do this diffusion models, etc., they do crazy stuff. Like these days, diffusion models are the state of the art, were considered state of the art, right?
So in that case, sorry. So in that case, they might release all of this as a foundation model. However,
it is a foundation model. That is what they say. If you look at the title of this paper, It literally says MovieGen, a cast of media foundation models. These are foundational models, and I think they intend to release it.
So like, the piece I'm trying to understand, Asif, is like, for example, whenever a software product is released, enough measures are taken into consideration so that someone cannot, pry it open and then figure it out and like, try to,
Oh, no, not in
replicate
the
it, right?
open source community. See, the research community is different, Pawan. The commercial software, when you do, you try to make sure that it cannot be reverse engineered and figured out, right? On the other hand, for example, that's one reason you don't put all your logic in JavaScript and ship it in a web page, because then people can read your JavaScript, right? But in the research community, the thing is the opposite. Researchers do marvelous things, and they hope there is at least one human being in the world who is interested in reading what they have done and understanding their discovery. So they write papers and they keep hoping somebody reads the paper, and they create this wonderful code and they put it in GitHub and open source it. And they keep hoping that somebody will find it useful. So the culture is very, very different in the research community versus commercial. And even in the, if you notice that, so I'll give you a paradox. If you look at Google, all of its products are behind, obviously, commercial products. They won't tell you the code base, for example, of Bigtable, right? They won't give you that. But if you look at their open source project, Unity's code base is in the open. But if you look at their DeepMind research group, right? They keep publishing paper after paper, and they give all the technical details. Each of these breakthroughs must have cost Google millions and millions of dollars in research, or tens or hundreds of millions of dollars in research, right? And you will not, but nevertheless, the research community has always been open, because science progresses or technology progresses when research community is open. So research community always makes its work available. The only company that I know which started the tradition of not releasing their research was a company whose name had the word open in it. So, you know what I mean? So, but they started this ugly tradition of hiding it all. But most companies release their research, and I would imagine that this will eventually show up ready for download and so forth. See, guys, here's the value of this paper. I'll just take a small interjection, and we'll take a break, because this is a paper that there's more details to it, and I want to go through it. It goes into flow matching algorithm. This paper puts two ideas together: a traditional architect transformer, autoencoders, and something called flow matching. Surprising thing is they don't use diffusion model. If you know about flow, normalized flows, and flow matching, which not many people have. In fact, if you pick up a typical textbook on deep learning, on neural networks, you'll probably not find a chapter on flow matching or normalized flow, which is a pity, right? And I teach it, of course, in the course, but most of the time, the fact that it is an alternative to diffusion model is a very powerful thing. It's, in my view, it's a generalization, and basically it does things better. It removes some of the deficiencies of the diffusion models, right? And the remarkable thing about this work is two things. First of all, nobody really thought seriously. Meta was not supposed to be in video generation, right? The Sora, what was the OpenAI's? Many of you have seen the Sora demos, right? Looks impressive, right? This big mammoth walking through the snow, and all of those demos, they look so impressive, except that Sora is nowhere to be seen, right? Then you have other commercial companies that do Runway and whatnot. They do video generation, right? They have a certain quality of video generation. They are diffusion models and so on and so forth. And then comes Meta out of the blue, in some sense, with this paper. And they just hit the ball out of the park in one shot. And they have a very simple architecture, no hacks. If you look at the latest diffusion models is a beautiful idea. I'll teach it to you in the afternoon. But the real implementations, commercial, has a lot of hacks back and forth and this and that to get it right. And for people, if you generate a picture of people, their fingers look right and so on and so forth. There are a lot of hacks you have to do, or many things you have to get right before you get the diffusion models to it. These people altogether avoid it. And they use a flow matching and normalized flows, a different mathematical argument. And they keep the architecture. While this may look complicated to you, trust me, this is a very simple architecture, actually. Right? And they get away with it. The most amazing thing is that with a simple architecture, in the very first implementation, they achieve the state of the art. They just hit the ball out of the park. So you realize the significance of something like this. These things are, in their own right, game changers of sorts. So now I have to get into the theory of normalized flows. So how exactly video and image generation happens? For that, you have to get into a bit of theory, but I'll get into it. But I want to show you. So upsampling is what I talked about, and the technical details of how you do it. I'll do that. I'll do that after lunch because your lunch is getting cold. This is a 93-page paper. If we go through every line, we'll be doing it till evening. And it's a beautifully written paper. But I want to emphasize some things. Look at this. We trained, and this is a thing buried deep in the paper. Please pay attention to this big statement. We trained the media generation on 6,144 H100 GPUs, right? Each running at 700 thermal watts of power, max power. Right? This is the thermal envelope with 80 GB HBMs. What are HBMs? High bandwidth memory, video memory. Right? So, for example, there are two kinds of memories you put on the video. When you get a 4090, you get a little more consumer grade video memory, VRAM. And when you get these enterprise grade GPUs, they have a slightly different memory called the high bandwidth memory, very high speed memory. So let's work it out, guys. One GPU, if you try to get in the open market, is about 40K. Right? So one H100 is 40K. That is 4 into 10 to the power 4. Isn't it? Right? And these people have used, give or take, 6,144. Let's make it 6 into 10 to the 3. Right? Multiply 6 dot something and change. Multiply these two together, approximately 25 into 10 to the 2.5 into 10 to the 8.
8.
Right? What is that looking like to you in dollars? 250 million, right? But that is just the GPU cost, right? If you look at the cost of the rest of the things, you're probably looking at some, right? Let's just say that they diverted $1 billion worth of resources, hardware resources, and says, okay, let's go train this model. Right? Just think of the sheer scale of investment that went into training this 30 billion parameter and the 13 billion parameter in those models. It was.
But they don't talk about how much time they trained it, right?
Yeah, they haven't talked about the time they trained it, but I think those things are easy to find out. We can get into I suppose they must be having a communication group where we can ask those questions from them.
Yeah, because what I wonder is that they might have built one big cluster of this, and they might be using it to train all of their models.
Yeah, that's how you do that. So I would imagine that this was trained for, let's say, 2 weeks. See, you're talking about 1 billion images and 100 million videos. It must have taken 2-3 weeks or a month at least to train. Right? And then, of course, you free up the cluster and you give it to someone else, to some other research group, because all the research groups typically are lined up. Right? So I remember when I was in grad school, we had the NPAC, Northeast Parallel Architecture Consortium. And if you wanted your job to run, your experiments to run, you had to give a long justification. It would get approved. And then you would get a budgeted amount of time on the supercomputer. And the worst thing that would happen is it would produce results, and then you realize that there was a bug in your code. And you don't get a second chance after that. So you have to be really, really sure. These are
Yes,
very
Asif, like when I did my master's, I went through a similar experience. And the most funny thing was when it was closer to the assignment submission, there would be so many jobs that were like, running on the machine that you wouldn't get any bandwidth.
Exactly. You know, in one of the original like big mainframe computers at MIT, something actually happened. They had a priority-based scheduling of jobs, right? So when they were decommissioning the machine, they found that there was one lowly graduate student whose jobs were submitted 5 years ago and never got a chance to be run because he was a lowly grad student. And it was deprioritized and it was kept on sitting in the queue. Yeah. So guys, then we'll come to the scale of the engineering part, tensor parallelism, sequence parallelism. So there's a lot of parallelism and engineering efficiency they brought in to expedite the computation, right? So I won't go into the rest of the paper, guys. This is a very well-written paper. It's very readable, but you need substantive background to understand all parts of it. I'm trying to give you some idea about how these things, for example, how video personalization is done and everything. It's a long paper. Let me not do that. It's time for your lunch. I will like to explain the two concepts of diffusion and flow, normalized flows. These are foundational. These days, image generation and this normalized flows are very, image generation and video generation are the rage, and audio generation. So it is worth asking, how are these done? Pretty much the scene is dominated by diffusion models and flows. If flows are coming in, I think this paper makes a big deal with flow. So it will take over, I think, in my view. So I'll pause here. It's time.